So we're going to adopt Einstein's solution, as verified by the Michelson-Morley experiment and many others since, that claims the speed of light as measured by all observers is constant. Since we derived the velocity addition formula by simple logic, we're going to have to change simple logic and intuition. There are many approaches to doing this. I find that the most useful one is actually a little bit algebra heavy, but on the other hand, leads to clarity. We're going to derive the Lorentz transformations that are the replacement of Galilean transformations. And so the next clip is going to use a bit of algebra. If you're uncomfortable or you feel that this drowns things out, you can feel free to skip it. The next clip will present the result and then discuss its consequences. But here, we're going to use only the assumption of the principle of relativity as applied to electromagnetism and therefore to the speed of light to derive the corrections to Galilean relativity that in the way that Einstein did. So, what are the Lorentz transformations? They are derived by the following idea. We have the statement that the speed of light is constant as measured by observers no matter what their relative velocity to each other. So we do the following thought experiment. We take our two observers. Remember, we had our two observers, the green axes and the blue axes. So we have one observer, x and t, whose measurements will be represented in black. And we have another observer, which was the blue observer, who is moving relative to the first observer at some speed. So this is the t prime axis. And what we're going to do is that at the same time as at the same instant as they're meeting at t equals t prime equals x prime equals 0, they both are at the same place at the same time. At that same instant, one of them, and it doesn't matter who, releases a pulse of light moving, say, to the right at speed c. And so, if you want, you can also emit a pulse to the left. The red line is therefore given by x, and as far as the green observer measures it, the red line is described by this straight line, x equals ct, because the light is moving relative to this observer with speed c. But, Einstein tells us, it will also be described by x prime equals ct prime. And this is going to be inconsistent, of course, with Galilean relativity. What does it tell us? Well, let's do some algebra. So we release this light pulse. One goes to the left, one goes to the right. X is plus or minus ct. Focusing on one of them will be quite enough. We want to understand how these two observers describe the position and time of the same event, some birthday party that happened somewhere. And so I'm going to claim that the position and the time as measured by the moving blue observer are going to be in some way dependent on the position and time as measured by the stationary, if you wish, the black observer. And these transformations have a few properties that I'm going to insist upon. One is, of course, that I want to insist that when x equals t equals 0, that was the instant that they met, at that time, that event is also the same as x prime equals t prime equals 0. This is just a way of synchronizing their clocks, and indeed these transformations have these properties. But this is not the most general functional dependence that has this property. This is called a linear dependence. I am assuming that x prime is some number times x plus another number times t, and likewise for t prime. The reason I want to do this is because this has the property that straight lines in the xt plane will be transformed into straight lines in the x prime t prime frame. We want this because we want physics to be preserved by these relativistic transformations. In other words, we want to know that an object that would be interpreted by the black observer as inertial, no forces act upon it, will also be interpreted by the blue observer as inertial. The property of moving at a constant speed, of having a straight world line, needs to be preserved by our relativistic transformations. So this is the most general transformation that has these two properties. And now, what are these numbers A, B, C, and D? Well, of course, in general, A, B, C, and D will depend upon something. What will they depend on? Well, they relate the black observer's observations to the blue observer's observations. What relates these two observers is the relative velocity v. So A, B, C, and D are arbitrary initially, functions of v, and our job is to find these four functions of the relative velocity v. So let's do it. What do we expect that we think we know about the relation between the black guy's observations and the blue guy's observations? Well, the first is that if you set x prime equal to 0, that's the here of the blue observer, well, that here should be moving to the right, say, with respect to the black observer at speed v. That's what defines the relative velocity v. And so setting x prime to 0 means we should discover that x is equal to vt. Okay? Put that into our equation, set x prime to 0, and what you see is that x prime equals 0 means that ax plus bt is equal to 0. That's the equation x prime equal to 0. I can solve this, and this says that x is equal to minus bt divided by a. This indeed describes something that is moving at a constant velocity. That constant velocity is negative b over a, so we discover that v must be negative b over a. The dependence of these coefficients on v is such that negative b over a is equal to v, or more elegantly, b is equal to negative a times v. Okay, we learned something about these coefficients. If I want, I can go back to my original equation and cross this guy out and write minus a times v times t. Okay, what else do we know? Well, there's this relativity story. If the observer in black sees the observer in blue moving with speed v, then of course the observer in blue must see the observer in black moving with speed negative v. In other words, if you look at the position x equal to 0, then that moves relative to the blue system with a velocity negative v. So let's plug that into our equations and see what it tells us. So when I set x equal to 0, I can see from my equation that when x equal to 0, I find that x prime is equal to b times t. When x is equal to 0, I find that t prime is equal to d times t. Remember, the idea is any event, x equals 0 at any time, should be such that x prime is related to t prime by this relation. The world line of the black observer is of something moving with velocity minus v. So I set these two to satisfy that relation, and I find that this means that x prime indeed is d over b times t prime, but that means that d over b should be negative v, or written more elegantly, b is negative d times v. And so that tells me, in fact, comparing these two, that d is the same as a. I can rewrite the equations implementing both of those results already, and I see a simplified form. A appears twice, 3 times in fact. We still haven't determined the coefficient c, but we haven't used relativity yet. We haven't used the idea that that light pulse is moving with speed c. Notice, so far, I haven't found any contradiction with Galilean relativity yet, but now I will. And what I'm going to find is the following story. So I want to insist that the light pulse, which is described, remember, by x equal to ct, that's that line, world line of something moving with speed c, is also described by x prime equal to ct prime with the same coefficient c. So now I need to plug all that into the current form of my equations. Let's try to do that. So if x is equal to ct, I find that x prime is equal to a times x is ct minus vt. And on the other hand, t prime is equal to c times x, which is ct. Sorry for the double use of c, at least it's clear in the typeset version, plus a times t. Now, I'm not so interested in t prime. I want to study c times t prime to make the comparison. So let's put another c here. Multiplying this by c, I get a c here. And now I see that when I set this is supposed to be equal to that, well, the ACT terms agree, so I can cross them out. The leftover pieces should agree with each other, so negative a times v times t should be c times the square of c, the speed of light, times t. Again, I can cancel off the t's, and I find that c is equal to negative a times v over c squared. Aha! That nails everything in terms of this one coefficient a, so let's write all that out. And we can plug that back into these equations, and this is what we've discovered so far. And this is what we've discovered. I have put back the velocity dependence of A, now that it's not too cumbersome. There's only one coefficient that contains all the information. All right, how do I determine this velocity dependence of A? Well, what I do is I have here two equations determining x prime and t prime in terms of x and t. I can invert them just as I did for the Galilean transformations and solve for x and t as functions of x prime and t prime. A little bit of algebra. You're more than encouraged to do it yourself, and you find that these are the inverse transformations that follow. I mean, if x prime and t prime satisfy these two equations, you can solve for x and t and get these two equations. Now, what do you expect? Remember, x and t are the position and time of a particular event as measured by the black observer, for whom the blue observer observes position x prime and time t prime. And so, remember, the black observer is moving relative to the blue observer with velocity minus v. So we know if Lorentz transformations, if our relativistic transformations are going to be correct, we know how to relate x and t to x prime and t prime. We basically repeat the calculation we did here, but with relative velocity negative v. In other words, this should be the same as that with the sign of v changed. So that's what we expect, that the transformation from x prime and t prime to x and t will be the same as this, with everywhere v replaced by the relative velocity negative v. Okay, that's great, because now lots of things look consistent. Look, the x prime plus vt prime cancels. That's reasonable. The dependence here is reasonable. It's only a question of this a of v and a of minus v. What do we know about a of v and a of minus v? A of v is the coefficient corresponding to moving with velocity v, say, to the right, or speed v, say, to the right. A of minus v is the coefficient corresponding to moving with that same speed to the left. The universe doesn't care if you're moving to the left and right. The universe, as far as we know, is isotropic. Left and right are the same thing. So we, in fact, expect a of v to be the same as a of minus v. That's because which direction you're moving in should not change the nature of relativity. What that allows us is to put a plus sign here, because we don't care. Multiplying through by a of v, we find that a of v squared, therefore, is equal to 1 over 1 minus v squared over c squared. Taking the square root, we have our answer. A of v is 1 over the square root of 1 minus v squared over c squared. Plugging that back in, we have derived explicitly the Lorentz transformations that form the core of the theory of special relativity, and we will be studying them carefully. We will be using them everywhere. And note that they are not the equations of Galilean relativity. Of course they're not. They have the property that with this change, the speed of a pulse of light as measured by the two observers will be c, and that violates velocity addition. So of course we've made a change. But Newtonian and Galilean physics worked very well. Where is the limit in which we reproduce Newtonian physics? The limit is clearly that if v, the relative motion, is very small compared to c, then I can pretty much neglect these denominators. This is much smaller than 1. These denominators are going to be approximately 1. And I find that x prime is indeed approximately x minus vt. And t prime will be approximately t, because v over c is a small number. So if I don't look too far away, and we'll talk about what that means in the next clip, then I am reproducing the Galilean transformations that make sense. The difference between relativity and Galilean relativity shows up at velocities which are not negligible relative to the speed of light. The reason that common sense does not agree with what Einstein predicts is because common sense is the intuition that we have developed over the course of our life, and over the course of our life we have not been walking around at speeds comparable to the speed of light. We have no intuitive sense for what this means, so we'll have to use math, and Lorentz transformations are the math that will make everything clear.